Hello everyone. Good morning. My name is Himanshu Agrawal, and I am being joined by my colleague, Dr. Rafal Dorosiak. So, we basically work at HELA, and we are dealing with the functional safety projects. And what my focus right now is to come up with strategies and ideas for the functional safety of machine learning and AI techniques, because until now we have good functional safety development life cycles for various other advanced driving assist systems. But for machine learning and artificial intelligence, there are some issues that need to be addressed before we can actually come up with some ideas like that. So yeah, in the recent decades, we have witnessed some great efficiency and performance of the AI-based systems. And on one hand, we have reached a point where we have plenty of ideas on how to impart the decision-making skills to the vehicle. But also, it is very equally important to obtain a good understanding in the safety perspective of autonomous driving. So we need to ensure that the autonomous systems are completely safe from any perturbations or maybe some irregularities that a vehicle might experience during its operation. So we see that automotive companies are right now quite interested in integrating more and more automated driving functions into the vehicle. But as a result of this, functional safety of such complex systems becomes quite challenging for us. So the aim of this webinar is basically to provide an overview on what are the challenges we face related to the functional safety of autonomous vehicles. And also we would see where the current ISO 26262 norm falls short in the development of autonomous vehicles. So we are going to highlight some of these important considerations, and then we will be talking about some safety aspects as well. So yeah, the agenda of our presentation today is that we are first going to address the motivation, where we see what functional safety is, and then why it is so important to us, and what are the considerations related to product safety in context of autonomous vehicles. And followed by this, in the second point, we are going to see the importance of interaction between different fields to ensure the development of safe autonomous driving functions. Then next, in the third point, we are going to throw some light on the sources of conflicts between ISO and machine learning. This is one of the core topics of this webinar. And then in point 4, we are going to provide a brief overview of the machine learning development process in context of the coverage with respect to ISO 26262 standard. And then another important topic would be that of point 5, where we are going to give certain proposals on how to use machine learning appropriately for functional safety. So we are going to talk about it using certain examples and situations. And then next, in the sixth point, we would mention in a nutshell some of the key points that are important to ensure an adequate amount of safety in automated vehicles. And then lastly, we would conclude with a quick review, and then would be open to any questions from the attendees here. So yeah, talking first about the main goal of the functional safety activities. So basically, the ISO 26262 vocabulary relates functional safety to the absence of unreasonable risk due to hazards caused by the malfunction behavior of E&E systems. These hazards could be due to some random hardware faults, some random software faults, and maybe the systematic faults during the development and in the production. So in this context, risk is defined as the combination of probability of occurrence of a harm and its severity. So in this graph, in the upper red region is the area where system risk with high severity and high probability of occurrence could be found. And in the lower left region, we see that the area of tolerable risk is there, which is basically the target of functional safety activities. So now the idea of functional safety begins with the hazard and risk analysis of such system risk. And the result is basically we have a list of safety goals with the ASIL level assigned to them. And then the initial system risk is reduced by certain technical measures, which we call as the safety concepts. So basically, the overall the concept of this functional safety activities is to basically reduce the potential residual risk to a tolerable dimension here. And at the end, we would get a safety case that shows that the safety requirements that are important for any system are completely met, and they satisfy the entire chain and the operations that are required properly. So yeah, talking about the general safety life cycle that we use for advanced driving assistance systems during the development and production. This is basically the safety life cycle that ISO 26262 generally proposes. So now we see that there are certain safety relevant functions in the system When we see some safety relevant functions in the system, we start with our functional safety management, which is basically this life cycle. So as you can see here, we have three phases, namely the concept phase, the product development phase, and the start of the production phase. So the concept phase includes basically the definition of the function on the vehicle level and the definition of safety goals. So we have the main results here as the item definition, the hazard and risk analysis, and then we also have the functional safety concept, which is very important. So item is basically a system or an array of systems to implement the function at the vehicle level. And then this hazard and risk analysis identifies and categorizes the hazards that the malfunctions in an item can trigger. And also we formulate the safety goals related to the mitigation of hazardous events here. And then we have this very important step, which is the functional safety concept, wherein we specify the functional safety requirements with the associated information and also their allocation to various architectural elements and the interaction between them to achieve the safety goals. This is definitely very challenging when it comes to machine learning or AI systems due to the complexity in decision-making algorithms. We would come to this point again in the further slides, but yeah, just to give an idea here. Then in the product development phase, we first have the product development at the system level, where the specification of the technical safety requirements basically takes place. And we also design the system here. Then based on the complexity of the architecture, the requirements for the subsystems are then iteratively derived at the hardware level and at the software level. So we can use here approaches like FMEDA for a quantitative evaluation of the hardware and maybe some software safety analysis for software architectural metrics. Further, we then validate these safety relevant requirements, the safety relevant functions to check if the safety goals on the vehicle level are qualified, complete, and fully satisfied. Then next we have this functional safety assessment step where we prove that the functional safety is met by evaluating various work products that we get throughout our safety life cycle. And we also review the implemented safety measures here by conducting several assessments at stages throughout the safety life cycle. So overall, the main outcome here is the safety case, that is basically the argument that the safety requirements for an item are complete and satisfied by evidence compiled from various work products of the safety activities throughout the development. For systems that are clearly understandable and less complex, this safety life cycle is very much adapted. However, for autonomous driving, we have AI and machine learning algorithms here, which makes it rather challenging to adapt the conventional safety life cycle. And why we say so is the subject of this webinar here, where we are going to highlight the barriers that makes this safety life cycle difficult for machine learning or AI techniques. So now we know that how functional safety is carried out, but why do we do it? Obviously, the public safety and driver safety are always of highest importance to us, but there are also consequences that companies are liable to in case these safety goals are not achieved. And these consequences may be economical or jurisdictional. So for example, in the economical consequences, we could have some economical losses with regard to the revenue, the market position, and the company's image. While from the jurisdictional point of view, the consequences range from both civil law and criminal law. By civil law, it could be the liability regarding warranty in terms of performance, quality, and durability. And then in the product liability, the companies are responsible for the compensation of the consequential damages and the losses. However, from criminal law basis, the companies could be imposed with sanctions in the form of financial penalty or prison sentence. So basically looking up at these consequences, one thing that we are pretty much sure is that the field of autonomous driving has to encounter a significant number of challenges before we could actually make them a reality. So building trust amongst the users and maybe the societal acceptance, safety, security, reliability. There's so much has to be done with regards to autonomous driving. And the development of strong AI systems has to be aligned with all such aspects to ensure that self-driving cars are totally capable of replacing the human drivers on roads. So yeah, now having said a little about the functional safety, I would like to talk about the norms that we use for assuring the product safety. So there are different areas of product safety, such as the safety of mechanical design, the safety of E&E systems, including the hardware and the software, and most importantly, the nominal performance. So for the safety of mechanical design, we have ISO 13489 norm for the safety of machineries. And for the case of mechanical design, we typically assume that the failures follow a viable probability distribution where we typically see no constant failure rate, as we can see here in the figure at the bottom left. For the safety of E&E systems, we have a very popular and well-defined ISO 26262 norm, which we use for functional safety of E&E systems to mitigate the unwanted and unreasonable risk. So unlike mechanical design here, the failures are assumed to have a constant failure rate in an exponential distribution. And yeah, you can see here in the graph as well, we have constant failure rates. Then next up is the most important context, also with relevance to autonomous driving, is the nominal performance. So however, we do not have any complete set of standards yet to claim nominal performance of the systems. There's already a SOTIF committee which is working on it. Nevertheless, we do have a preliminary first draft, which is the ISO 21448 draft, but a lot of further inclusions are still to be made. For this, we are in constant touch with the working groups and the members from various organizations through conferences, and we exchange ideas on the SOTIF approach for the autonomous driving. So typically this requires working hand in hand with the OEMs, and yeah, we have to include a lot into the SOTIF aspects for assuring complete safety of autonomous vehicles. So yeah, now coming to an important point here is talking about the safety of autonomous driving. So this requires an intervention and quite a good efficient synergy between various fields. The three important fields, like the first field is the AI ML, which is obviously the most obvious case, and then we need to also have a good background on the functional safety as per the ISO 26262 norm. And the last one is the SOTIF, which is the safety of intended functionality. As I said, it's still in progress and not completely developed, so we have to talk about it in detail. So yeah, the first thing is development of ML AI algorithms for autonomous driving. We develop algorithms, we then test them and test their behavior in different platforms. And next up is the functional safety, where the idea is basically to ensure that there are no safety goal violations due to hazards that are caused by random hardware, software faults, and the systematic faults. We follow the safety life cycle that is in general. And as we saw in the safety life cycle, we had a phase which was known as the functional safety concept. So with relevance to that, we develop here the technical safety concepts and also the hardware and the safety concepts in the functional safety. Then the next one is the SOTIF thing, which is very important in autonomous driving. So here we deal with the advanced concepts of the complex automated driving architecture. So we also discuss here the approach for evaluation, the verification and validation of SOTIF related risk. So basically at the end, we must have a criteria, we must formulate a criteria so that we can have a smooth release of autonomous vehicles into the market. And then we need to have a efficient synergy between all of these fields. So talking about the first interaction would be between the interaction between functional safety and AI ML, which is the agenda of this presentation as well. So here the idea of this interaction is basically to develop and implement some machine learning techniques by avoiding systematic failures. Also in this presentation, we are going to propose some ideas on how we can use machine learning appropriately for functional safety. So that is the core idea of this interaction in the red box here. So we define here the functional requirements for risk assessment and also talk about the confidence in the software tools that we are using for designing our algorithms or maybe for collecting data for our training. And like in general, for functional safety, we have technical safety concepts, hardware and safety concepts. But for when we have these AI systems into consideration, then we also have to develop some safety concepts for ML and AI exclusively. So we need an exclusion of the steps in the process via this interaction.
So I would like to emphasize this slide is very important one, yeah, because as I see, we have now 69 participants, and probably not all of them are daily doing functional safety topics in their work. So it's important to emphasize this functional safety ISO 26262 standard It has been already several years in, let us say, in development. 2011, there was the first edition published. In the last weeks, the second edition. So this is kind of established. But as Mr. Agarwal said, what we are talking here about are systematic software faults. For instance, to get a very simple example, infinite loop, because I'm programming very complex loop and I don't even, as a programmer, able to see that that I programmed something that in some cases could get into an infinite situation, or maybe some use of pointers that is, let us say, not correctly programmed, and during the execution the software is jumping into memory areas that it's not allowed to jump, and so on. These are the examples of the systematic faults, which means they don't occur randomly, they occur because the programmer obviously he didn't know that he did it, but he programmed them into the software. Then for the hardware, we have also systematic hardware faults, because we can also do the hardware design if we don't consider all of the rules in a manner that that something could go wrong. And also there we have random hardware faults, like for instance, short to ground, open, and so on, or bit flip in the memory, in the RAM. So these are the cases that are covered by the ISO 26262. By the SOTIF, which is called Safety of Intended Functionality, this is kind of a new topic. We are also there working in the VDA and ISO in the working group since several years now, preparing that. And in this year, there should be a publicly available standard published on this topic. Here, it's important also to emphasize, here we are speaking about the situations where we assume there are no faults, like the ISO 26262 considers them. So no systematic software faults, no systematic hardware faults, no random hardware faults. But anyway, we get into problematic situations because, for instance, one of the biggest examples that is considered in SOTIF is because we are using technologies that are limited, like radar, camera, LiDAR. We are not able to 100% to know that the environment has been recognized correctly. All of these technologies has pros and cons, as probably the majority of the participants know. And here the focus is, even if we assume hardware, software is everything correct, that we are also able to cope with the limitations of these technologies. And of course, this topic that is today in the focus of the presentation, artificial intelligence, machine learning, it is, if at all, in the both two other areas considered a little bit. There are some interfaces, but especially this is also, let us say, there is no silver bullet solution yet. There is no standardization. Everybody is struggling with the topics because we don't have, let us say, the deterministic software development anymore. Himanshu will also show in the presentation. In the classical neural network, we are not even able to, let us say, take a look into this black box and check how the decisions are made. Then also the topics of trainings data, how to cope with that, how to make the topic at the end of the day safe, that there is no potential of violating the safety goal, no potential of giving harm to people and environment. So these are the topics that are for us very challenging. We also see in the whole community that everybody is struggling with this and doing research on this topic. So this is going to be the focus of the following slides in the presentations. So Himanshu, please continue with your slide flow, and I look forward for, let us say, for the rest of the presentation, where we will see also practical solution proposals from our side that we have worked out.
Yeah. So yeah, Mr. Devasiak has already given a brief overview of everything in this slide. So basically in this presentation, we are not going to deal right now with this screen interaction, which is the SOTIF and AIML, because as he said, like there are lots of technological and system performance limitations, and we have to come up with ideas on how to develop this SOTIF measures against such triggering events, which are the problems that are caused in sensors, algorithms, and actuators. But for the time being in this presentation, we are going to focus only on this red and the brown channel, that is the functional safety and AIML. And also we would be addressing some of the conflicts between ISO and machine learning, what's there, what's not there. So talking first about the brown channel, the sources of conflicts between ISO and machine learning. The first one is the nominal performance. This is an important agenda of this presentation. We already saw a glimpse of nominal performance when we were talking about the product safety in the previous slide. But let us for now consider nominal performance measurement as simply detection versus time. So in the graph, you would see that this true positives detection and the false negative detection. You see that for nominal performance, we see that the false positive detection is quite low, and which is very good. Similarly, the true positive detection is significantly good with a little miss rate delta. However, when the nominally performing system is subjected to some random hardware failures or systematic faults, we see a significant degradation in the nominal performance in the detection results basically. So we see that the false positive detection have relatively increased. On the other hand, the miss rate delta is now higher. This is a very serious concern when it comes to functions in autonomous driving from the safety point of view. We refer to this situation as degradation of nominal performance, which is quite not desirable in functional safety. But the issue is that the ISO 26262 standard does not address the aspect of nominal performance at all, because of which we cannot completely prevent this degradation to happen. So this source of conflicts demands an absolute necessary interpretation in ISO 26262, such that when we perform the functional safety in automated vehicles, we can completely prevent the corruption of this nominal performance. That's the first source of conflicts that we mentioned here. The next one is the technological limitations, as Mr. Dorosiak also said. So these limitations are related to the sensors, algorithms, or the actuators. So here we would like to take an opportunity to give one such example. So we have as of now an ideal image captured by the camera. We call it ideal in the sense that our decision-making algorithm is capable of accurately processing the sensor data to yield important information related to environmental perception. The sensor can see the road curvature or the lane marking or maybe the objects around it. But now when it is subjected to certain perturbation, for instance, here we see that the perturbation is the overexposure of the sun rays on the camera lens. Just for now, assume that. So as a result of this perturbation, the data from the sensor would look something like this. This perturbed image due to the overexposure of sun rays is a very serious safety concern for decision making, as the learned system would completely overlook the lane markings, the lane width, and also the road curvature. So now that's clearly a technological limitation. And since most of the decisions in autonomous vehicles would be based on non-deterministic algorithms, such situations are a matter of serious risk and concern in safety argumentation. But unfortunately, ISO 26262 standard does not consider such technological limitations. Hence, addressing this source of conflict in the future release of ISO or SOTIF is a subject of utmost importance. This involves development of adequate SOTIF measures in the future, and the future guidelines would help us in establishing a more rigorous framework for functional safety. But as of now, it's an open subject. So yeah, next conflict we would like to talk about is related to the safety requirements management. So conventionally in functional safety, it is very important for us to have well-defined and unambiguous requirements. Only then it is possible for us to trace back the right side of the V model to check if the left side turned out to be proper or not. But for autonomous vehicles, it would be rather challenging. For instance, talking about the machine learning or AI techniques. In case of AI ML techniques, the requirements would be different from the conventional form of requirements. For instance, the requirements for machine learning would be that of the training data set, what neural architecture has to be used, or what should be the approach that we use for training, the internal neuron activation functions, weights, etc. So it's not clearly what we see in the conventional requirements. So as a result, defining them formally and clearly itself is a big challenge for us, owing to the black box nature of the decision-making neural nets. So this non-determinism in the decision-making would pose a significant challenge for the requirements management of autonomous vehicles. So yeah, so as said, the conventional verification and validation techniques in ISO would not be sufficient, and as per the ISO 2626 norm, and we have to talk about the functional safety of automated vehicles in another aspect, which is the SOTIF. That's again another source of conflict. So yeah, now since autonomous driving technology significantly depends on machine learning for applications such as object classification, signboard detection, etc. So it is crucial for us to address these typical steps related to the development of ML systems. Also, evaluation of these steps would help us in finding ways on how the systematic faults could be avoided in ML system. So these steps are partially adapted from the ISO 21448 SOTIF draft. So yeah, beginning with this process, the first step is the collection of the training data using real world on-road examples, the test scenarios, and the simulation. This is followed by labeling the training database for specific features that are to be learned, such as road boundaries, vehicle type, and etc. The label data is then used in the configuration steps where the parameters or the weights in the learning network are determined via training procedure. Then the result of the training has to be then verified with the training data itself as a maybe as a pass fail criteria, or maybe something like a acceptable false positive rate and false negative rate. So this step is called self verification. But obviously, in case of discrepancies, the entire chain of steps can be restarted to collect more training data and or to modify the training approach. Quite evidently, this self-verification won't be sufficient, and therefore there lies a need for a separately collected database, which is our verification database, and the corresponding labeled one. This is basically done for cross-verification. So the results that we obtain from the trained network using both training and verification database are then used for the evaluation and determination of the nominal performance. This is basically a general approach towards ML development. However, there are many training limitations and issues that can be uncovered into it. So these steps are of critical importance for the safe operation of autonomous vehicle. And from the safety point of view, we would expect that our data is collected and the learning network is developed as per the safety standards so that we can avoid the possible hazards. So talking first about the software tools used for the collection of data, they need to qualify the ISO 26262 standard. So basically in ISO there is a part 8 which exclusively deals with the software tool qualification, and it checks if any error in the output of the tool introduces some sort of other errors in the safety related item. And other than that, we have the software development that has to follow the ISO 26262 norm. So part 6 of ISO 26262 deals with the software development level. As we have already seen in the previous slide, within this process, something that's a big issue for us right now is the nominal performance, because that's not covered by ISO 26262. So this step would require intervention of maybe some sort of aspects, but as of now, it's excluded by ISO 26262. So now we would like to give some proposals on how we can use machine learning appropriately for functional safety. So in this segment of presentation, we are going to mention some of the important considerations. Obviously, the requirements for AI system would mainly be related to the training and verification data sets, and thus the proposals we present here would basically reflect or focus on the idea of strengthening the data collection or maybe carrying out a systematic data handling. So the first one in our list would be the independency between the training and verification database. So for a safe decision making, we would expect an unbiased learning process. From the safety perspective, it is of critical importance. Therefore, at data collection stage, we must investigate and implement ways to achieve higher degree of independence between the training and verification database. So one way is to acquire data from different suburb environments or different architecture of roads, buildings, houses, pedestrian networks, etc. So for instance, here we exploit the data acquired from the Oxford robot car dataset, and we plot the GPS traces in the graph. The green ones here are basically the GPS traces from the training data, while the purple ones are the GPS traces from the testing data. Also in the red, we would see here some proximity points of test data with respect to the training data. They are in the same direction. So these are the points where we can say that there is little or no independency between the training data and the verification data. So these and the testing data. So these proximity points would be undesirable for our ML development process. So the idea is to always check for independency before using this data in our formal ML development process. And also, depending on risk, further restrictions could be imposed after a discussion with the safety analysis team. And so this is very important from that point of view. The next one in our list is the aspect of adequate coverage. So many would agree that it is something that is often very challenging to acquire as there are innumerable situations or rare case scenarios that a human driver can encounter while driving. So translating all such scenarios to an autonomous system would be rather very challenging as they are humongous in numbers. So nevertheless, a safety argumentation is incomplete without addressing this issue. So yeah, adequate coverage, as I said, the database must have a good coverage taking into account diverse aspects. These aspects could be like the localization, the type of area, adverse weather conditions, daytime, season. So enhancing the coverage is important, and maybe we can have some synthetic data generation that can be used for enhancing the coverage. We can use something like generating adversarial networks. I hope many would be knowing already about it. So yeah, we can use something like this, but maybe we would have to make them very much efficient and robust for synthetic data generation. So for example, this is just an idea that we can propose maybe a GANs to be used for adverse weather condition, and I'm sure like many of us would already be knowing about it. So yeah, suppose we already have some training data available, so we can synthetically add the effect of different weather conditions on the training data, such as rain, fog, snow, mist, plenty of them. So when we have these effects added to our training data, then we can have a new set of synthetic data, which is now we have like triple the number of available data. So right now, if it was 100, we would have now something like 400 training data with the aspects of various weather conditions embedded into it. This is possibly one approach, but I'm sure this would require a lot of work that has to be done with the development and making it tuning the hyperparameters properly. But yeah, this is just a proposal, just an idea that we can use. Yeah, another important point is the labeling process, which is also one of the proposal on how we can use machine learning appropriately for functional safety. And labeling is always a big issue for people dealing with the machine learning or artificial intelligence. And obviously, the systematic failures in this labeling process would very much affect the nominal performance of our system. So yeah, we have to make sure that this labeling process is good and efficient. Maybe some ideas would be methods would be some peer review of the label data. Maybe you can define a fraction of labels for each algorithm, and you can choose these fractions depending on the risk, the level of risk that you are imposed to. And also, in case of high risk, you can have some redundant labeling by independent persons or maybe some different algorithms. So idea is basically to make sure that this labeling process is free from any errors so that we can prevent our nominal performance to get corrupted. Another important point is the up-to-date data. This is equally very much important when we're talking about the safety considerations. So what about when there are some new trends, even in the development phase when we come across some new trends, for example, LED traffic signs or new vehicles such as street scooter, and also we have to make sure that our system also knows about this thing. For example, in the image we can see here that will a pedestrian detection still work with the new trends in fashion? This is equally important to consider. So idea here is basically even when your system is in production, you need to continuously monitor the nominal performance in field. But how frequently do you monitor it, and what would be the intensity of this monitoring? That could be chosen independence of how critical that particular aspect is. So yeah, but that's equally important when you uh, monitor this nominal performance in field during the production, so that we have completely up to date data at every time. So just an overview, we have talked about here the four proposals related to the collection of training data sets and how we can systematically handle the data. These four are independency. Then we talked about the adequate coverage. We also spoke about the labeling process and also the up-to-date data. So yeah, at the end, just see a kind of accumulation of all the ideas that we have presented here. So for ensuring that we have a complete safety of automated vehicles, we need uh, these six important points from the safety point of view. The first one is systematic data handling. Here we would avoid the systematic failures by ensuring that we have adequate coverage, independency, efficient labeling process, up-to-date data that we already spoke in the previous slide. Then next step would be completeness. We must have a complete description of the system and what are its abilities. We must have well-defined specification and requirements, which is obviously very challenging, but from safety point of view, it is very much required. We must have good knowledge about the components that we use here and the interconnection between the various components. The next one would be transparency. As safety engineers, we must have good knowledge on how these complex decision algorithms work. So how basically any particular decision is made, or maybe how the features are selected in autonomous context. So all this information is very much required for us. And as I said, we must have some robust strategies to deal with the inherent complexity in machine learning and automated driving, such as we have to deal with adversarial perturbations and also with various environmental conditions like fog, rain, snow. So all basically these aspects have to be considered when we are designing a machine learning algorithm. So for safety, obviously, we would have to perform a rigorous functional safety analysis. This would basically, the idea here would be to mitigate the random hardware failures and the systematic failures, as Mr. Dorosagi also said in his slide there. So we have to make sure that all these things are mitigated and we completely satisfy our safety goals. But as I said, functional safety as per ISO 26262 is not enough for machine learning or AI processes. So also we need to address the safety of intended functionality. So here the interpretations in ISO has to be made to accommodate machine learning. As we said in the slide there earlier in the interaction slide, the green channel that would address the malfunction that are arising from various technological and system performance limitations would be made here. We would come up with some accurate, some good efficient SOTIF measures so that we can avoid these foreseeable misuse and some performance limitations in the system in context of autonomous driving. So yeah, just brief conclusion. So we had spoken about the functional safety activities, which deals with the mitigation of risk due to random hardware faults, software faults, and systematic faults. However, in case of autonomous driving, the technological and system performance limitations can pose significant risks to us. Then, as I said, the safety of self-driving vehicles would demand an efficient synergy between the fields, AI, machine learning, functional safety, and ZOTIF. We also address some of the sources of conflicts between ISO 262 and machine learning. So the traditional approaches or the conventional approaches of verification, validation, and the approaches for assessing the software safety are not sufficient for the AI or ML development process. And also we spoke about the development process of machine learning, and we also saw its coverage with respect to ISO 26262. And then we made some proposals or ideas on how to use machine learning appropriately for functional safety. We just gave a few ideas related on how to efficiently collect the data and label them properly, but there are many more possibilities, and we have to dig up this particular interaction between AI, machine learning, and functional safety even further. So also we propose some key points, the 6 points that we mentioned that are very important to argue safety in automated vehicles. And further elaboration and common understanding has to be established in the community prior to including all these things into ISO and SOTIF standard. So yeah, for us, the further scope of the research would lie in the formulation of the SOTIF measures to deal with the unintended behavior and the system performance limitations. So yeah, that is from our side. And yeah, we would be now open to questions. Thank you so much for your attention.
Thank you very much, Himanshu and Rafal, for these interesting insights. Now would be the time to ask questions. It's my hint for the audience. So if you have anything burning, if you are wondering about some things from the presentation, please don't be shy. Yeah, ask your questions, just type them into the panel. We are happy to discuss them. So far, I have one point here from one guy of the audience who was giving some kind of a hint, just a hint regarding SOTIF. The ISO PAS 21448 is officially published since January 16. Is that something that you were aware of, Himanshu?
Yeah. We know about it.
All right, perfect.
Yeah.
Apart from that, do you spot any questions that you would like to address, Himanshu or Rafal?
Also, like there's something which we can talk about here in the. So basically, when we talk about this ML development process here, so again, an important point from safety point of view would be to define something known as algorithmic fairness. For machine learning people, I know it's a broad thing that has to be formally described, but yeah, from the safety point of view, it is equally important for us. So we would expect a good formal description of what algorithmic fairness is, so that we can have we can do a rigorous analysis of the safety considerations with respect to that. So yeah, this is just one point about algorithmic fairness that I would like to add here.
Thank you. Now we have two more questions from the audience. Leonie, do you want to read them out?
I don't see the questions.
I have a question regarding slide 20.
Maybe I think there was some issue with the audio at the moment. Could you read it out again?
Absolutely. We have a question regarding slide 23. How do you plan to check and test transparency? Could you answer that, Himanshu?
Yeah, I got you. Okay, yeah, I know it's not possible to for neural networks to have a good idea about the transparency, but at least we should have an idea on how the algorithms work and how the decisions are made, how the features are selected. So obviously, I understand it's a black box feature of the neural networks, but we have to do a safety analysis of the decisions making. So we must know what are the strategies that you're using for decision making, what kind of architecture of neural network do you use, what are the neuron activation functions you're using, what approach you use for training. So we need to have a transparent idea of all such things when we do our safety analysis in that. But yeah, we completely understand the point of black box feature, so that's not an issue. But there
is
should be a good.
basically one of the biggest challenges. Yeah. So
Yes.
Who asked the question? Mr. Stefan Henning. Yeah. So you picked out one of the biggest challenges, definitely. Yeah. So also we probably don't have the silver bullet solution today, but we would handle it similarly to Zotif. So test a lot, validate a lot, and what today is also, let us say, very often in the functional safety field to be seen is that we don't really have a big trust yet in such machine learning topics, and that there is always a second channel built in a deterministic classical way. And at the end, there is a comparison, and in case of any deviations, we go into the safe state. Yeah, that's the current situation. But for autonomous driving, we need to get better on that, of course.
Okay. Thank you. Now, the next question is there a standard tool used by Hella qualified for FUSI or AI ML algos?
No, as of now, nothing. But this was just a proposal that when we design any system, so the software tools that we use, basically, we follow the ISO norm. So we have a dedicated part of ISO norm that deals with how we qualify a particular software tool. So for AI/ML, we don't have any software tool as of now to check, but we have to follow the guidelines related to ISO for whatever software tool you're using for acquiring the data. For example, when you use some camera, so we have to use these norms and check if camera qualifies the software standards that are required for as per the ISO 26262 norm. But as of now, it's nothing. It's an open subject right now.
So basically, we qualify the tools that we are using on our own with our software tool qualification process. But it's exactly like Himanshu said. As for today, we don't have a qualified tool with a stamp, with a certification or something like that. We are working on that. We are evaluating different tools as well. Yeah?
All right. Then the next question is about the labeling process. Why do you need labeling, and what is the purpose of the labeling process? Maybe you could give a quick answer to that.
Yeah, in case of supervised learning, I think we would mainly focus on supervised learning in this aspect. So yeah, labeling is often what we see generally. Labels are not properly assigned to any training data set. And when you feed these wrong labels into the system, so there would be problems related to classification, for example, or the decisions that are made at the end. So this is why we say that the labeling process has to be perfectly done with regards obviously to supervised learning. This is the question this is the thing that the person wanted to ask, I guess.
All right. There are a few questions more coming in. So another one would be, do you need the information for networks such as 5G?
Yeah, why not? This would be because as you would be progressing in when you would be progressing in neural networks and their development, then obviously we would also have to parallelly think on the safety aspects of each and everything. So it's basically the knowledge transfer between our developers and what we do as safety engineers. But obviously, there are lots of we can see that every day or maybe every year we see a lot of advancements in what neural networks are made and how the approaches are used for making them more efficient and robust. And parallelly, what we do is we consider each and every aspect and see what are the safety considerations related to what you guys develop in machine learning. So yeah, it's obviously very important always to parallelly check them.
Yeah.
So we could also say 5G will be central for autonomous driving. We need always to differentiate a little bit what is possible today and what we will need to cope with in the future. Yeah? If we take this big picture with car-to-car communication, car-to-infrastructure communication, of course, 5G will be also a big aspect. Then there is, let us say, to put it simplified, the challenge between the offline learning of the or teaching of the network and online one. Yeah, is it allowed to continue to learn the network also during driving when the end customer has the car and so on and so on? Can I in the future also use the information from the car to X communication for learning for training the network and so on? But these are all future topics, definitely, and everybody is struggling with these topics, and we need to, of course, do it stepwise.